In this lecture, I will be reviewing neutralization reactions. These are acid-base reactions where the proton, or the hydronium ion, is neutralized by a base or a hydroxide. Case in point, in its most simplest terms, from an acid, we have a proton that's either transferred, okay, and we have a hydroxide from a base or from water that became a hydroxide. And essentially, what we have here is this proton will combine with a hydroxide and form water. And when that occurs, we say that the acid that generated the H plus or the base is neutralized. Now we know the neutral pH is when you have equal amounts of H pluses and hydroxides. We know that water naturally breaks apart into these two compounds, or these two ions, I should say. Water self-ionizes and breaks down into an H plus and a hydroxide. And we can write it two different ways. We can write it as two water molecules colliding together and making the hydronium ion, H3O plus, not sure why the O was up there, plus the hydroxide. These are synonymous, as I've talked about before. And the equilibrium, or the KEQ, which we've learned is the products over reactants, coefficients become exponents, solids and liquids don't apply, is essentially equal to the products over reactants, as I just said. And we know that the KQ for this reaction is very small. In fact, it's a special reaction for what water does by itself. We call it KW. And KW is equal to 1 times 10 to the negative 14. This means that water barely does what? It barely goes forward. If this is a very small number, that means that the reactants are favored at equilibrium, which means that the water is acting like a very, very weak acid. It barely dissociates. It stays together. And that's why water is a terrible electrolyte. There's just not enough free ions to conduct electricity very well. And we say water is neutral because normally one water breaks apart into one H plus and one hydroxide. So that must mean that when you multiply them together, we get two numbers equal to the same, 1 times 10 to the negative 7 times 1 times 10 to the negative 7. And we say the pH of the H plus, the pH is 7. So if you take and neutralize an acid with a base, or neutralize a base with an acid, what we're really saying is we're matching up the hydroxides with the protons. All the hydroxides match up the protons exactly, and what you're left with is water. Now, why do we make water? Well, think with me for a second. If the KW is so small, that means the equilibrium position for this reaction favors the reactants, which means if you add too many of these H pluses or H3O pluses or hydroxides, any combination of these, we know that the Q is going to be larger than the K. Remember that? So we've got this little thing where we got the K and all reactions go toward equilibrium. So if the Q is larger than K, meaning you have what? More products than you're supposed to, the reactions favor the K and go backwards. So because this number is so small for the KW, oh, Christmas in July, I meant to do this, because this number is so small that it's easy to have more H pluses. Remember, this number represents Q being smaller than K. So this would represent the value of area you could have for some combination of H pluses and OH minuses. This number being so small, any number bigger than that would put your Q, or your reaction quotient, behind the equilibrium position that's so small. So it's almost impossible to have this small value. So anytime you have any H pluses or hydroxides, they're going to go in the reverse to do what? Make the water. And if you don't quite get all of that, it's very simple, people. If you have a small Ka and the reactants are favored, and you add more products by Le Chatelier's principle, by increasing these values, won't they shift to the left and make more water? Of course it does. Many ways to look at this. So when you hear the word neutralization, you're thinking that we're matching H pluses with a hydroxide. Now, not all neutralizations are perfect, as I'm about to show you. Some neutralizations are. And if you can match all the H pluses from an acid with a base, you'll be left with a pH equals of 7, because if you match all the H pluses that are available with exactly the amount of hydroxides necessary to make what? Well, these two would make 2 water molecules. You'd be left with just the water you started with, which would have naturally that much H pluses. And that's why a neutral pH is 7. And that's why they call it neutralization. You're going to take out all the extra base with acid or extra acid with base to get neutral water back. All right, and that's the essence of neutralization, matching hydroxides with protons. So let's look at some of the reactions, okay? And they're all very similar, and they look like a reaction we've already done before. For instance, I have a hydrochloric acid. Now we know this is a strong acid already, and we write aqueous to say that it's in solution, but you know what? This is a Kardashian wedding. It's not together. It's really what? It's really an H plus and a Cl negative. This base is not really written together. By saying aqueous, and I know this is a strong base because I've got a hydroxide with a group 1 ion. Group 1 ions are always soluble because their charge densities are so low. This is Na+, and this is OH-. They're free. So when you pour these guys together, well, my friends in chemistry, once the H pluses hit the hydroxide, for the reasons I just explained, you're going to force the water to form. So we're going to make water, and you can write it H2O, but you could also write it HOH. The reason why HOH is helpful because it makes you think about the H in front doing what? Donating to the hydroxide, or an H plus hooking up with a hydroxide to make HOH. So if you can see it as water, be my host and put it that way. And be my host, not my guest. If you're my host, well, then you just kind of take care of me if you come to my house. So in any case, moving forward, what else is going to happen? Well, the Na and Cl, okay, I guess come together. We write it this way on a Regents level, and it would also be aqueous, so it's not really free, but essentially these would be spectator ions. In a higher level course, we'd write a net ion reaction. We're not doing that here, though. Okay, so the chemical names, this is going to be hydrochloric acid. You could also use the IUPAC name of hydrogen chloride. This is sodium hydroxide, right? That's the IUPAC name. Hydroxide is the polyatomic ion. And this is sodium chloride, IDE because it's binary. And this is dihydrogen monoxide, or we can just use this as water. Okay. What I want to get after, though, is what kind of reaction is this? Well, this is neutralization, but I can't say enough. This was an H plus and a Cl negative. This was an Na plus and an OH negative. What just happened? The H plus found the OH, Na found the Cl, sort of. This is a double replacement reaction. Hey, the ions are just double replacing. We call this neutralization because the ions we're dealing with, or these ions are coming from, are acids and bases. So this is a type of double replacement reaction where the proton from the acid hooks up with the hydroxide to reform not necessarily a precipitate, but something like a precipitate that doesn't like to what? Break apart, and that's your water. Okay? And this would be liquid. And then these ions are spectating, or we write them together to show that they're dissolved. So the biggest thing here is that this is really like a double replacement. And you need to understand that it's also an acid plus a base always gives us a salt and water. And that's really important here. Now, the approximate pH of the resulting solution is going to be 7. And the reason is essentially we matched all the H pluses with the hydroxides. And what was left over, the chloride ion and the Na plus, have no ability to ionize water. As we talked about before, the chloride ion and the sodium ion are really conjugate bases and acids of the strong, like for instance, Cl negative is a conjugate base of a strong acid, which means it has no ability to pull H's from water to create a hydroxides and reform the acid. And Na plus has also got to, again, its charge density is so low, it's not going to do that as well. So we say that the pH is 7 and neutral. Now on the reagents level, we would just say, hey, an acid and base, if you add equal amounts of them, and in my worksheet here, I'm saying I'm equaling 0.1 molar of each. Okay, so I'm adding 0.10 molar of each of these. So I'm adding just as much H pluses as hydroxides. So therefore, they would neutralize. Okay, next one. Why don't you try that yourself? Try to make a double replacement reaction, name it, and figure out the acidity. And you should stop me now. Okay, I'm back, and I took my acid and my base. I split them down the middle to see where my ions are. Here's my proton, here's my nitric acid, the conjugate base part of the acid. Here's my K plus, my OH minus of the strong base. And I double replaced them. All right, just matched up what? This positive with this negative to make the what? The salt. Salt's an ionic compound. And then I matched the what? The proton from the hydroxide to make the water. Acid plus base makes salt in water. Okay? The name is nitric acid, but I also could have used the IUPAC name, hydrogen nitrate, potassium hydroxide, potassium nitrate from table E, and of course water. All right, so it's very simple. We've done double replacements before, but you have to realize acid and base makes salt and water. All right, now moving on to number 3. Now number 3, we're dealing with an acid that's not a top 5, let's say, in our tables of Kas. This is a weak acid. Okay, it does not completely dissociate. However, as we'll learn in AP, a strong base, it's an alkali metal with hydroxide, strong base, can force this to completely dissociate. But in any case, let's see what happens here. We know we can split these right down the middle. All right, so this H will go with this OH. Now this is not OH2 bonded, it means it's 2 hydroxides. All right, this is a dibasic base. So anyway, one H plus hooks up with 2 hydroxides to make water, and let's write that there, HOH or H2O. And then we have calcium, which we know is plus 2. And if this lost an H, this is the acetate ion, which by the way is listed in table E, and it's C2H3O2. And it's -1. I know it's -1 if I go to table E, or I know it's -1 because it loses an H+. Calcium is plus 2, so I need 2 of these. And now we have to consider balancing. 2 here, 2 here, 2 H's. Okay, I need to do this. And now I'm balanced. Okay, and an acid plus a base. This is acetic acid, or you can say hydrogen acetate. And this is calcium hydroxide. And this is calcium acetate. Of course, this is water. And bottom line is acid plus base makes salt and water, double replacement. We have to watch our balancing. I kind of mention that here, but everything was a 1-to-1. 1K, 1K, 1 nitrate, 1 nitrate. Everything worked out here and here as well. Now, you may think, Mr. Grodsky, all the base hydroxides matched all the protons, and we've got neutralization. And you would be right to think that. And we did. We neutralized all of the acid with the base. The only problem is when the weak acid, okay, was neutralized by the strong base, what did we produce? Well, think with me. We had this H, C2, H3O2, and what it produced was C2, H3O2 negative in a proton. If this is a weak acid, as we've learned already, this must be a decently strong conjugate base, right? If the Ka is low, The Kb has to be higher. So what we're saying here is that we have a base that significantly can absorb protons or pull protons from water. So this will absorb. So C2H3O2, okay, around water can pull the H pluses from it and produce the hydroxides. So at neutralization, we will not be at 7. We will be at something greater than 7 because the base will yank H's off water. Now, if you don't like that, think with me for a second. If I've got a strong base and a weak acid, doesn't it make sense at neutralization I will be basic because a strong base is a little stronger, if you think that way? The real answer is that you're creating a conjugate base that has an ability to yank H's off of water and reproduce some hydroxides. Now, it's not a lot because not a lot of acid was what? Dissociated. Only a little bit of acid comes off if the Ka is small. These two acids are what? Strong acids. So they completely dissociated because their conjugate bases had no ability to reform the acid. So of course they'd be 7. Something to think about as we go further. All right. Now, what are the net reactions? Now we can continue this, and you should try number 4 on your own, check the key. But and of course number 6 is very similar, except number 6 you have to use the what? The products, right? HOH came from what? H pluses and hydroxides, and this is K plus and CO3, so you can reform the acid and base knowing the salt and the water. And number 7, this is very important. What's the overall reaction of 1 and 2? Well, in number 1, if I'm not mistaken, sorry to make you go crazy, I have HCl and NaOH. Well, HCl breaks apart into an H plus, maybe, and a Cl negative at some point. Okay, and I'm going to do this up here. For some reason, the bottom it does this. So I have HCl, which is H plus and Cl negative. The base is Na plus. Reason why I'm writing them broken apart is because they're strong. And what happens? Well, they double replace, and they make Na plus and Cl negative. And guess what? This finds each other to make water. Now the NaCl is really separated. I know we write it NaCl aqueous, but it's a spectator. So if you can think about this, Na plus and Na plus here, and Cl negative and Cl negative cancels because they're not doing anything. What you have, which will go down here, is an H plus from an acid plus a hydroxide gives you H2O. That's the overall bottom line in neutralizing a strong acid with a strong base. Okay, sometimes this is called neutralization reaction. I know they say an acid and base makes salt and water, but this is also considered neutralization. Okay, hope that helped.